Okay, now let's take a look at some common interactions and the resulting forces. So first of all, two objects with mass are attracted to each other gravitationally. This is called the force of gravity. The direction of this force will always be along the line connecting the two objects. It's directly toward the center of the other object. Now, two objects are pressing against each other, scrunching the atoms. So if I press on the table, or even if an object is sitting on the table, this pen is scrunching the atoms in the table. And then due to that contact pressure between them, the table is scrunching the atoms in the pen. And we can see this with this model, that if this model represents the atoms, these red objects represent the atoms in the table, and the springs represent the bonds between the atoms. If you set an object on the table, there's some deformation that happens in those bonds. The molecules and the atoms are moved, they're compressed, and they want to spring back to their initial position, creating an upward force. Likewise, if this is the object set on the table is pushing up then on these. So for example, if this is the hand pushing down, you can see there's deformation in that top object as well. So the name of this force for today, we're just going to call this the scrunchy force, but it will get a more scientific sounding name next week. And the direction of this force is perpendicular to the contact surfaces. So the direction of the force of the table on my hand would be upward. Third, two objects are in contact causing shearing, a sideways deforming of the atoms. This is the friction force. And what this means is if this is the table and you're dragging your hand over the table, you can see what's happening to the atoms in the table. They're being sheared to the right. So the friction force is causing the friction interaction is causing a friction force to the right on the surface of the table, but that force is pulling to the left on my hand. So the direction is parallel to the table, parallel to the contact surfaces, and opposite the direction of the motion or intended motion. Okay, the fourth force is a string or rope between two objects is taut. That is the tension force, and the direction is parallel to the string. And lastly, when a spring or other elastic material is stretched or compressed, if it's actually a spring, we call it the spring force. If it's something else like a piece of elastic, a rubber band, a piece of plastic, or rubber, we would call it the elastic force. And the direction of this is parallel to the spring or the deformation. So let's do some examples now, applying what we've learned about diagramming forces to some everyday, or maybe not everyday, situations. So first we have a man on a vine. In class we had an action figure hanging from a string. So here's a string, here's the person. System schema diagram. What objects do you think are important in analyzing the man? We have the man in bold type here, so he's the focus object. The focus object is underlined. So we have important objects being the man, the string, and now we need to start considering the earth. On our system schema diagram, we're going to show all interactions involving the focus object. So those are all the objects that are interacting with the person. You could, go beyond this and put, the chandelier, because in my house this is hanging from a light fixture. But you don't need to include that because it's not interacting with the man. So we have the string interacting with the man, so draw an interaction line. We have the earth interacting with the man. And then on these lines you can write what kind of interaction. This is tension, that's a string, and this is gravity. Okay? And the man is our focus object, so we're going to put a dotted line around that. And now we're ready to draw a free body diagram. Show the object as a dot, draw all the forces, and label each force. So we're going to represent the man as a dot. And now we're going to draw each of these forces. I can tell there are two forces because there's two interaction lines. So let's do this one first. The string is a force, and if I look back at the picture, I can see that the string is upward, so that means that the tension force is upward. Label it with the names of the objects. This is the force of the string on the man. And then I also have the force of the earth on the man. That's pulling downward. And because he's at rest, these forces, and there's only two forces, these forces have to have equal magnitudes. So this is the force of the earth on the man. Okay, so that is our free body diagram. Now for the second example, we have a cup on a table. So the objects will be the cup, the table, and the earth. And we need interactions now. So I can see that the cup is touching the table, so I have an interaction there. That means, that reminds me that there's a force of the table on the cup, but there's also a force of the cup on the table. And that is a scrunchy force. They're scrunching the atoms due to that pressure of the contact. And then we have the cup and the earth. These are not touching, but this is one of those forces, the interactions that happens at a distance. And that is called gravity. And our focus object is going to be the cup. So now moving to the free body diagram, we represent the cup with a dot, and we look to see how many forces are on the cup. So I see that there are two forces, and I'm going to start with this one. Force of the earth on the cup is downward toward the center of the earth. And then I have this force of the table on the cup, and that's upward. And you might want to draw that upward force, you know, like this, like it's under the cup or here. But we want to draw all of our forces with the tail of the force on the dot. So it's going to look like this. And that is the force of the table on the cup. Okay, notice that we're mentioning the objects here that are interacting. And these forces have equal magnitude because there are only two and it's at rest. So I can conclude that they must be balanced. Also, when you're doing a free body diagram, notice that you're only including forces on one object. So this is on the cup and this is on the cup. All the forces on this picture should be forces on the cup. Okay, the third example. A block is on a horizontal surface. A block on a horizontal surface is pulled with a horizontal string. The block doesn't move. So we have, what are our objects? In fact, go ahead and pause the video and try this one. And then after you're done, continue the video and check and see if you end up with the same thing that I have. So my objects are the block, the table or the surface, the string, and the earth. I don't need to include the hand because the hand is interacting with the string, not with the block, and the block is my focus object. So I have the block is interacting with the string, that's tension, and the block is interacting with the earth, that's gravity. Now with the table, there's this scrunchy force going on because there's some pressure between them. But there's something else going on too. The fact that it doesn't move tells me that it must not be perfectly smooth surface. There must be some friction. So there's another interaction also going on between the block and the table, and that's the friction or the shearing interaction. Okay, we're ready to do our free body diagram. So choose your focus object, which is going to be the block, and count the forces. 1, 2, 3, 4. So I should have 4 arrows on my free body diagram. So here is the block. I'm going to draw the string force first. Force of string on block. And then pulling to the left, that's going to be the friction force. And I know these have to be equal because it's not moving and these are exactly opposite to each other. So force of friction, and the objects were that it was the table on the block. Okay, and then we have the force of gravity. Once again, I don't know how the force of gravity compares in size to this one, so you just have to make something up. Force of the earth on the block. And then we have this scrunchy force, which is perpendicular to the table. So that's this way. And that's the force of the table on the block, but that's the scrunchy interaction. And these two are equal to each other because those are exactly opposite to each other and it's not moving. Okay, that concludes the examples that we did in class, and there are 2 more examples posted in Edmodo.